For TrackML, the idea was how can we make something that's lightweight, that helps people understand the problem intuitively, using what we humans are very good at, which is pattern recognition.
So machine learning is not new to us in the field. What we try to do is to simplify the problem to some extent, that it's understandable for someone without having a real high-energy physics background.
We see the current algorithm being at the edge of what they can do, and that's why we are looking outside, looking for different approaches.
We are on the verge of a breakthrough. We feel that it's actually important to probe and ask the data science community for even more novel ideas on how to tackle the problem.
The TrackML challenge, what we want to do is to expose the problem to as many different people from different backgrounds as possible. Tracking is a very expert field in the high-energy physics. People have spent their lives doing this. But at the same time, there are many algorithms popping up everywhere in science and in machine learning. And the best way to connect these experts with machine learning people is to do a challenge.
It would be very interesting to see if out of these we could come out with, let's say, an original point of view into this problem, which is it's a relatively old kind of problem for energy physics.
We're always interested in getting expertise from outside of physics and seeing what people in other fields can teach us.
We have points which we need to connect together, and we can have an approach which is can call a brute force approach, just try all possible connection. But it turns out there is a 10 to the 500,000 connection, which is an enormous amount of possibilities.
And here comes the physics, and that makes it such a compelling problem. So in our standard way of analyzing a single collision, 99% of the reconstructed objects is uninteresting once we found it.
Designing a new machine learning algorithm from scratch requires a high level of abstraction, much like mathematics, but applying to a problem, a very complex problem, with very different inputs, very different effects, this, I think, is the thing which we know how to do.
Nowadays, there is a growing trend of applying more deep learning in all stages of the data processing of high-energy physics data, and it's just because the initial tests that were done are actually very promising and are bringing deep improvements to the previous methods.
It is clear that this is the one element that I see, maybe with Genoma, that can really change our society on a time scale of a few decades.
In the end, a lot of what we do as humans is understand and process data, and so a lot of what we do as physicists is just we deal with maybe more data than most people are used to, and so we've got some skills that are perhaps a bit even ahead of what's going on in industry.
Strong mathematical, statistical skills, programming, presentational skills, flexibility.
It is not always clear from people from academia what they can bring to the private sector, but indeed the wide range of skills, the scientific rigor, and the ability to adapt to new problems are, I think, characteristics of people in academia that would be really beneficial in industry.